Limit of a function refers to a value a function approaches at a certain point. So suppose I have a function, I want to find what value it has at point x equal to 2. So I want to find limit x approaches 2 of f of x. In this case, I can look at what value the function approaches as it comes in from the left-hand side. And let's say that value is 1. So then I will have limit as x goes to 2 from the left-hand side of f of x is equal to 1. And then I can look at the limit from the right-hand side, say the function approaches point 2 from the right-hand side. So clearly we see that the limit as x goes to 2 from the right-hand side is going to be also equal to 1. So if the right-hand side limit and the left-hand side limit are equal to each other, then we can say that the limit exists and it is equal to 1. So this is just an example. Now I will do some problems to further illustrate the concept. So for problem 1, I have the following graph. So the limit at point x equal to 1 of our function f of x, to find the limit of our function f of x at a point x equal to 1, I would need to consider the right-hand side limit and the left-hand side limit. And we can see that as we approach the function, as we approach x equal to 1 from the left-hand side, we are approaching value 1. So limit as x goes to 1 from left-hand side of f of x is equal to 1. And looking at the right-hand side limit, we see that it approaches value 0. So limit as x goes to 1 from the right-hand side is equal to 0. So we see that the limit from the right-hand side doesn't equal to the limit from the left-hand side. And therefore, the limit does not exist. You can use D and E as a shorthand for does not exist. So then looking at point x equal to 2, so limit from right-hand side approaches 1, and limit from the left-hand side of f of x also approaches 1. So because the limit from the right-hand side and from the left-hand side are equal to each other, the limit exists and is equal to 1. Now I will look at point x equal to 3. So here limit x as x goes to 3 of f of x. So I will use the same technique where I'm looking at the limit from right-hand side and left-hand side. We see that limit from the right-hand side, approaches value 0. So the limit from the right-hand side at x equal 2 is equal to 0, while the limit as x goes to 2 from the left-hand side of f of x also approaches 0. So limit from the left-hand side is equal to 0. Therefore, the limit exists and is equal to 0. Note that the value at x equal to 3 does not need to be defined, or it does not need to be equal to the limit, as long as from the left and from the right the function approaches the same value, the limit exists. In other words, if there is a pointwise discontinuity, then the limit can still exist. Now I will look at a different example. So for problem number 5, I'm given limit x goes to 0 of a function x over absolute value of x. Now I am going to graph this function. So the graph of this function looks like this. We see that at x equal to 0, the function is discontinuous. Note that from the right-hand side, x divided by x, absolute value of x, is equal to 1, while the limit from the left-hand side is equal to -1. Because the limit from the right-hand side and left-hand side do not equal each other, the limit does not exist. Now we'll look at another example. Here I am told that the limit of a function f of x when x is equal to 1 is equal to 5. And it asks, must f be defined at x equal to 1? And the answer is no, as we saw in a previous example. For example, at point 3 in this function, although the limit existed, the function did not need to be defined at that value. So I can say that as long as left-hand side and right-hand side limits at x equal 1 exist and are equal, limit will exist and the function does not need to be defined at x equal to 1. Alright, so now I will do a problem that looks at finding the limits numerically. Here I'm given a function g theta equal to sine theta divided by theta. And I'm asked to compute limit as theta goes to 0 of this function, g theta. So I can rewrite it as limit theta goes to 0 sine theta over theta. So the graph of this function looks as the following. So it's clearly a well-behaved function at point x equal to 0. However, it has a pointwise discontinuity at x equal to 0. So if we look at the values of the function numerically, so I'll have a theta on top and g theta on bottom. So when theta is -1, g theta is equal to 0.84. At -0.5, g theta is equal to 0.95. And at value -0.1, the function is equal to 0.99. And similarly, at value 0.1, it's equal to 0.99. And 0.5, it's equal to 0.95. So we see that the function from the right-hand side and from the left-hand side, the function approaches the value 1. So we can conclude that function is equal to 1. because the closer the point that you look at, the closer the value will get to 1, and eventually it keeps trying to get to 1, but it never quite gets there because the function is not defined at x equal to 0. But we can sort of see where it's going, and it's going to value of 1. Then another technique for finding limits is limits by substitution. And here we'll do a problem. Solid 26. And here I'm asked to find limit as x goes to -1 of 3x squared over 3x minus 1. So usually when a function is defined and continues at a point, we can just look at the value of the function at that point, and the limit and the value will equal each other. So plugging everything in, I get that it's equal to 3 minus 1 squared, 3 minus 1 minus 1, which is going to be 3 divided by 3 minus 1, and that's equal to 3 minus 4. When a function is not discontinuous at a point, then its limit is equal to its value.